2010 Mechanics NCEA Level 2 Physics Question 5. The spectators. Aroha has a mass of 55 kilograms. She steps onto a bench to get a better view. The bench is 4.0 meters long. And 3 millimeters appears to be the flex in the bench. You can see that it's dropped in the middle where Aroha is standing on the bench. When she gets onto the centre of the bench, it bends downwards not just 3 millimeters, 3.00. That looks suspiciously, there we go, high in significant figures. And our answer, calculate the spring constant of the bench to the correct number of significant figures. Okay, so important information we're going to require for this is the mass of Aroha, this 3.00 millimeter shift. Remember, we need to use SI units, as it's talking about, correct SI units, and we should make use of the correct significant figures. But the SI unit, this is 3 millimeters, which is 0.00300 meters. Meters is the SI unit. So F equals Kx is the equation that we need to use. And we're looking for the spring constant K. So K equals F over X. The force applied is not just 55. 55 is her mass, but mass is nothing without a gravitational field acting on it. When the gravitational field of the Earth acts on it, it becomes 550 newtons, or you could do 55 times 9.8 to be a little bit more specific, but I'm just going to stick with this for my calculation. I don't know what the correct calculation is used in the answer, but anyway, and X, the displacement of the bending bench, is 0.00300, and that will give you an answer of the spring constant, 1.8 times 10 to the 5, because we've got that tiny number on the bottom. It's going to make the overall number a bit larger, quite a bit larger, times 10 to the 5 newtons per meter. Newtons per meter is the correct units for spring constants. So that's the SI units. B, calculate the elastic potential energy stored in the bench. Now, if you remember, elastic potential energy, or any potential energy, is the work done. Work is force times distance. However, we can't use this. Why can't we use this? Because the force changes according to the displacement from F equals Kx. So we can't do that. However, we have to use the area under the graph, and there's another formula anyway, which you can just go to the formula. But the reason why we don't use work as force times distance is because of that changing force as the distance or the displacement increases. So we have to use the potential energy, elastic potential energy, is half Kx squared. And we plug in our numbers. Half is half, K is what we just calculated up above, 1.8 times 10 to the 5, and X is 3 millimeters, but remember we put it in 0.003 squared, and that will equal 0.81 joules of energy stored. Okay, moving on. C, or not quite C. Aroha then walks towards one end so that she's 1 meter away from support B. Okay, 1 meter away from support B, and the bench is in equilibrium. Explain what this means. Okay, this is equilibrium is defined with two equations. I'll write the equations and then I'll talk about them. So sum, that's what that sigma, capital sigma, means. Sum of the forces equals 0. That means all the downs and the ups and the lefts and the rights and the backs and the forwards are equal and opposite to each other, so there is no net force. And the sums of the turning forces, or the torques, also equals 0. So there's no acceleration in a rotational direction. There's no rotation going on, which tells us that the sums of the torques also equal 0. So both of those statements are required for the correct answer there. Oh, do we have to explain what it means in detail? There's a lot of space there. You don't actually. That covers it. The marking schedule is relatively brief as well, but I guess it takes a while to write that down if you're writing it down in a little bit of detail. But video, quick, you can hear me talk about it and it's easier. D. Support force B exerts a force of 120 newtons on the bench. Assuming the bench is uniform, calculate the mass of the bench. Now, that's interesting. I'm going to have to shrink down our picture here so I've got the whole thing in. Sorry if that's lost some information for you because of the resolution of the display, but you just have to listen to how I talk about it. So I'll go to green and we're going to work on the right hand side here. So this is D. So support force B is exerting a force of 120 newtons on the bench. That means it's upwards. So 420 newtons. Aroha is acting with her force of 55 times 10, 550 downwards here. At the centre of the bench, the centre of mass of the bench, you've got the mass of the bench times by gravity, which is what we don't know. We don't know the mass of the bench, and that's what we're trying to find out. So from this we can come up with some equations. Best equation to use, and there's also a support force A, which we don't know either. But we're trying to find this. This is what we're trying to find. G is going to be 10 or 9.8, so we can, once we know this force, we can just divide it by 9.8 and find the mass. So it looks like the easiest thing to do is use our sum of the torques equals 0 Newton meters. So 0 equals all of the clockwise torques minus all of the anti-clockwise torques, and it's probably a good idea to, since we don't know this one, to make that our pivot point. Okay, so that's our pivot point, drawing a little triangle to show where we pivot. So that's a 0 distance times by the support force A, which means we can ignore that as our as a force, as a torque. Sorry. Okay, so clockwise torques is going to be 10 m times by the distance across here, which is half of the length of the plank, 4 meters, minus the 0.5 meters that it's coming in, because that's where the pivot is. So it's 3.5 meters. So times 3.5. So that's a plus. And we're also adding on to that, Aroha is 1 meter in from the end. And let's see, between the two supports must be 3 meters, since you've got 0.5 and 0.5. So 3 meters. So she will be, if she's 1 meter in from the end, that means it's 2 meters to her here. So it's going to be 550 times by 2, which is the force times the distance. Okay, there are no downward forces. But there is an upwards force, which is the 420 newtons upward at the full 3 meters from the support A, and this is in a different direction, so we're going to call it minus, and it's 420 times by the 3 meters. Okay, so excuse me. So what we're going to do then is just add all those up and cancel out to find what m equals, pretty much. I'll do 10m first, and then you can see how the progression works. Okay, so taking these two parts here, we end up with minus 160 in the first part. So 0 equals 10m times 3.5 is 35 m. So that means 35m equals 160. So m equals 160 divided by 35 gives us 4.5 or 4.57, 4.6 kilograms. Now I just want to check that because something's bugging me here about this. My intuition's ringing bells about something wrong. Okay, I see what I've done wrong. I used 3.5 meters for some reason for this distance here, when clearly it can't be 3.5 meters because the whole length is 3.5 meters. Remember, we worked out it's 3 meters between the two support forces, and the mass of the plank is going to act halfway along that, so it's actually 1.5. Correction, so it's going to be 1.5. That means it's going to be 15m and 15m divided, so 160 divided by 15 gives us 10.6 recurring. So 10.6 recurring, which we round to, let's see, everything's two significant figures, so probably 11 kilograms is the mass of the plank. And that's the answers and the answers as well, which I just did a big check before to make sure I hadn't got anything else wrong. And yeah, fantastic. You'd get slightly different answers if you used gravity. The gravitation acceleration due to gravity, force due to gravity is 9.8 kilograms per newtons per kilogram compared to 10 as I've done. You'd get closer to 12. Yeah, but anyway, that's how you do it. Oh, and that's the end too. So all the best for your exams if you're using these to study for your exams, and I hope you've enjoyed using the Physics Lounge to look at these things. Check out the rest of the stuff and recommend to your friends, please.